Hi guys and welcome to this next video. We had just discussed the compression members in steel design. And we have discussed the different formulas that we can apply in the analysis of compression members. Now we'll be covering an example. Okay, so this is the problem that we are going to solve. The built-up section consisting of W350 by 90 with 12 mm plates is formed into a box section as shown. The section is used as a column 10 meters long. The column is fixed at both ends and braced at mid-height about the weak axis or the y-axis. And we have the following properties that we have here all on our table below. And this is what our column looks like. So we have here the red part, that's the W350 by 90, having the flanges shown here, including the web, and we have the plates at both sides. So if we're going to attach the plates here, it will now form what we call a box section. All right. Now let's have let's move the figure here over to the left, make the font here a little smaller, and we will now look at the solution that we're going to apply to solve for the allowable axial capacity of our column. And we'll be covering all those different formulas that we have discussed in that first video. Make sure to watch that video. If you haven't watched it, please visit our channel. And once again, please don't forget to like the video and subscribe to The Online Engineer so that you can continue to learn engineering online via YouTube. All right. So let's now consider the solution to this problem. Okay, so I have here the given that we have, as we could see from our table down below over in properties. So I just have it there. We have the flange width, we have IX, we have the depth of our section, as well as IY, flange thickness, the area, TW, and TP. That's equal to 12 mm. All right. So just a few things. In one of our discussion earlier, we're able to consider some key principles or key terms that might be asked for problems like this. Well, as you can see here in the question, it just tells us determine the allowable axial capacity of the column. Well, in the flow of our solution, we'll be able to cover that as well. But what about if what is required first is some very basic or key elements that we might need to answer? Such as, for example, what if the question is basically asking us for the effective length factor that we could apply? All right. So these are pretty basic principles that we need to fully understand, guys, no? So that we could also determine the right values for L and K that we're going to use in the next parts of our solution. So what about effective length factors that we are going to use? Well, we take note on what's happening over here. So you might notice that the column is fixed at both ends and braced at mid-height about the weak axis. Okay, so when we talk about fixed at both ends, you might recall that we have a table earlier that shows that if we have fixed at both ends, then the K that we are going to use there is equal to 0.5. We're able to recall that? All right, we showed a figure that when we have fixed at both ends, K is equal to 0.5. Now, as we all know, the section that we have over here, as what you can see here down below, has two axes, and that is the x-axis, of course, as we can see here. This is our x-axis. And of course, we have our y-axis as what we can see here in our figure. Now, the x-axis is considered the strong axis of section. It's because most of the time sections are designed or proportioned in such a way that the section has a big IX, or the moment of inertia, making the x-axis stronger than the y-axis. All right? That is why when we talk about bracing, as what is mentioned here in our problem, the bracing is usually applied along the weak axis. Okay? It's most of the time applied on the weak axis and not on the strong axis. Okay? So this is what we're going to do. First, we consider that an effective length factor could be applied here of 0.5. And we take note that this is um, considered for the x-axis. Okay? So once again, if you try to analyze this, guys, along the x-axis, what do we have? We have fixed on both ends of our column. And when this happens, then of course, we have a k value of 0.5. All right, no problem with that. Okay, what about for our y-axis? Well, for our y-axis, if you try to think about it, yes, we still have the fixed support at both ends, guys. Take note of that. However, we have bracing at the mid-height. So how does bracing look like? Actually, bracing is just considered as a pin connection. Okay? Take note of that. A bracing point is basically considered a pin connection. Okay? It's considered a pin connection. So if you're going to analyze this, if this is now your unbraced length, let me just mark this up to you guys so that you can see. This is now the unbraced length in the y-axis because as what we know, when we say unbraced length, it's the length between 2 points of lateral supports. So our unbraced length for the x is of course the total length of our column, while for the y-axis, we have 1/2 and 1/2 of the total length. How do we know that it's 1/2? Well, it says here that there is bracing at the mid-height. And once again, the bracing is a pin connection. If it's not mentioned, then you can safely assume that it's a pin connection. Okay, so what do you think is our k value to apply for the y-axis, guys? Well, the k value that we're going to apply here is 0.7. The reason for that is going back to our unbraced length. Okay, take note. Let me just mark this up for you guys. This is now our unbraced length. I'm going to call this Ly. All right, unbraced length in the y. Same thing with the one here below. This is now our Ly. So if we consider the unbraced length, we have here a pin connection. And at the bottom, we have here a fixed connection. So what would be the k value if we have a pin and we have a fixed at the other end? K value there that we can apply is 0.7. Okay? So these are not required in our problem. This is not the question of the problem, but these basic principles, guys, mind you, very important for us to be able to determine the slenderness ratios later on. Okay, so these are our effective length factors. Now, let us consider now our slenderness ratios. So sometimes the question has to do with the slenderness ratio of our column. So let's now consider the discussion for the slenderness ratio. Well, the slenderness ratio would now be considered for each of the unbraced lengths that we have, because in generally speaking, the formula for the slenderness ratio, guys, is K times L all over the radius of gyration. Now, we have basically two axes that we are going to analyze. So if you're going to consider the x-axis, I'm going to write this as S or X over here, guys. And this would be Kx times Lx over Rx. All right, let me just make that quick correction over there. All right, so it's Kx Lx over Rx. Kx is 0.5. That's we have mentioned earlier. And Lx, guys, is the total length of our column, which is 10 meters. Okay, so we have Kx here. We have Lx. So what do we need next? That is the radius of gyration. Now, the radius of gyration that we are going to use is for the entire section. Now, the properties here that we could see is actually the property of the W350, because it shows here the flange width, the total depth, the thickness of the flange, thickness of the web, Ix, Iy, and A. So these are properties of our W350. The 12 mm plates have not yet been included in the consideration of these properties. Therefore, when we talk about the total Rx that we are going to use here, guys, then the formula for this would be the square root of the Ix total of the section divided by the total area of our section. So let's now consider this two. All right. Well, the easiest to consider first is the total area, and that will just be the area of our section that we have here plus 2 times the thickness of our plates times the depth. All right, let me just show here our answer in terms of mm squared. That would be 19,950. Okay, so once again, that's the area 11,550, which is given in our properties that we have here. Okay, and we have the thicknesses of our plate, that's 12 mm, and of course, the total depth of our section happens to be the total depth as well of our plate. So I have it multiplied by 2 because there are 2 plates on both sides of our steel section. All right, now let's now consider Ix total. How do we consider Ix total? Well, we already have Ix of the section, so that's good to go. But we have also to include the contribution of each of these plates that we have here on both sides. So each of these also contribute to the total Ix of our section. Okay, so take note their centroids lie in the same x-axis. So we could simply just add the effects of our moment of inertia. So that would be Ix plus 2 times, what's the Ix of a rectangular section? Once again, this is 12 mm over here as our thickness, guys. 12 mm with the total depth D equals 350. All right, so that's a rectangle. Formula for that is BH cubed over 12. So that would be PP, which is our thickness, times, I'm going to multiply with this with the depth, cube over 12. All right, so that would now give us mm raised to the 4. So our answer here is 35175. What's this? Now, let me just express this according to, there you go, times 10 to the 8, 3.518 times 10 to the 8 mm to the 4th. So that this is now our Ix total. We don't need to transfer moment of inertias because they all lie on the same x-axis. So they are both aligned on that same axis. All right. What do we do next? So we have here Rx. Simply, we have square root of Ix total divided by the total area. In terms of mm, our Rx is 132.784. Okay, so we're able to follow that. Going back to this formula that we have over here, this is now Kx Lx over Rx. Kx, we already had Kx earlier, that's 0.5. Lx is 10 meters. So I think we can now have our SRx defined finally. So that's Kx times Lx divided by the Rx that we just had. And that is 37.655. All right, so that's SRx. Now, aside from SRx, we also need to determine our SRY. Now, what is SRY? So that's KY times LY over RY, of course. So this is the effective length factor. This is the unbraced length of our column LY, and of course, our radius of gyration along the y-axis. Now, our LY here is how much? If our Lx is 10 meters, we're going to go back here. We have defined Lx as equal to 10 meters. For this specific problem, guys, Ly is equal to 5 meters. And the reason for this is what? Okay, so we consider again our problem, and we see here that we have the bracing at the mid-height about the weak axis. So our Ly, the one that we have here, is just 1/2 of our total length. So that is why we have here our Ly as equal to 5 meters. That is. All right. So let's proceed. We have ky, that's 0.7. Ly is equal to 5 meters. What about our ry? Well, ry, in our solution for this ry, we recall the procedure that we did earlier. That was for Rx. And this time we're going to repeat that for our Y section. So this will now be equal to Ky times Ly. This is the square root of Iy total divided by the total area. Okay? So the total area, we had that already. That was 9950, considering the effects or the contribution of those two plates that we have on both sides. All right. Now, what about for Iy total? This is what we're going to do to solve for Iy total. For Iy total, take note, we are going to take the moment of inertia with respect to the y-axis of our two plates on both sides. All right. So we're going to transfer it to our y-axis. Our y-axis is found here at the middle. This is the centroids of our plates. So we have to transfer this towards our y-axis. This will now involve transfer moments of inertia. Okay? So Iy total will now be equal to what? This is Iy, right? Plus, let's now consider the transfer moment of inertia for these two plates. So that is 2. This is to consider that we have two plates, both sides of our section. All right. And then we'll consider the centroidal moment of inertia of one rectangle only. If you recall, what is the Iy of for a particular rectangle such as this, for example, having thickness and having depth. So Iy here is, what's the formula? Okay, I hope you still recall your formula. That's dTp cube over, well, so in the same way, we apply that principle over here. So this is the depth times Tp cube over 12. Okay. And when you transfer moment of inertia, what do we do? All right, let's apply the transfer formula. So we're going to add in the area of the plate. So that's d times Tp times the distance of transfer. This is from the center of our plate that we have over here. Where can we see that? This one? From the center of the plate going to the center of the entire section. Because this is where the y-axis is located. So we simply transfer, okay, the moment of inertia from this central point of our plate to the center of our section. So what's that distance? The distance from the center of the plate to the centroid of our entire section. This x distance that we need to consider. So what's that x distance, guys? If you can consider the different properties that we have, this is BF. That's the flange width, right? I'm going to use that here. This is now BF over 2, so 1/2 of the total flange width, plus TP over 2, and I will have this squared. All right. So this will now be our total Iy total. So in terms of value, I can have this equal to, let me just change this unit over here to mm to the fourth. That's 188,793. 188 million, I think. 793,200 mm to the fourth. I could even have this expressed in terms of scientific notation. All right. So that will now be my Iy total. No? We're still not yet done. Let's now have our Iy total divided by the total area so that we can have our radius of gyration. So that will now be 97.20. Okay, 97.20. Okay. After this, we can now solve finally for our slenderness ratio with respect to the y-axis. That's ky times ly, and we divide that by ry. And that will be 35.979. Okay? So, what is our maximum slenderness ratio? So, I'll have it here. I'll call it SR maximum. So this is the maximum of SRX and SRY, which is 37.655. SRX, the one that we solved earlier, 37.655. SRY is 35.979. And this is now our maximum slenderness ratio. Okay? Maximum slenderness ratio. So what do we do next in our step-by-step process to solve for the allowable axial capacity? Okay? What do we do next? Well, we discussed that in the previous video that we had. We had SR max. Now, we are going to compare this with the quantity known as CC, okay, which is defined in our NSCP book as the square root of 2 pi squared times E over Fy. Okay? So that would be 2 pi squared E over Fy. Okay. So, by the way, we have E and Fy, which are needed values. So let's now consider an E value of 200 gigapascal for our steel and an Fy value of 250 megapascal. Well, these properties of steel need to be provided, so just substitute them as they are provided in the problem. Okay? If there is no E provided, then you can safely assume for steel that's 200 gigapascal. But for Fy, you have to consider what is the value of Fy that is given in the problem. There are different grades of steel. Some are 250 megapascal, some is 345 megapascal. For this problem, let's consider this particular given information. All right, so Fy is 250, E is equal to 200 gigapascal. So our CC is 125.664. What do we do next? We're going to make the comparison. So the comparison here is for SR maximum, which is 37.65, and for CC. Well, we can see here that SR maximum is actually less than CC. What do we do next? What we're going to do is to get the ratio of SR maximum and this value of CC. And that ratio here is 0.3, 0.2997, or 0.3. Okay? The next step is to solve for what we call the factor of safety. The formula is 5/3 plus 3/8 times A minus 1/8 times A cubed. And the answer for this is 1.776. Okay, so that's our Fs. Now, what do we do next? We now come to the point where finally we're going to solve for the allowable stress for this column. And that would be Fa, now have 1 minus 0.5 A squared, all right, times Fy over Fs. And finally, we have our allowable stress. Let's just express this in terms of megapascal. So that's 134.471 megapascal. Now, this is in terms of stress. Sometimes what is asked is the actual capacity of our column. When we say capacity, this has to be in terms of load, in terms of force. So PA is now FA multiplied by the total area. And finally, guys, this is our answer. This is 2682.694 as our final answer for the problem that we have over here as the actual capacity of our column. All right. So I hope you understand. You've learned a lot of things from this video. Feel free to pause the video at different points when we had our discussion, and feel free to rewind to those parts where you probably need to understand first, and to refer to the previous video or to refer to your notes so that you could follow every step of our discussion. All right, so if you have questions or any comments on our presentation for today, feel free to do it below, comment in our video. And once again, please don't forget to like and subscribe to our channel, The Online Engineer, so that you will continue to learn more about engineering I'll be focusing on steel design. I'll be focusing on structural engineering subjects and civil engineering, but I'll also be considering discussing topics in mathematics and in the engineering sciences. All right, see you guys. Till the next time.